Verdu, who's visiting us from Princeton University. Sergio is one of the prominent members of the information theory community. He's a winner of many awards, the Shannon Award, which is the leading award of the IT community, and the Richard Hamming Medal from the IEEE, which is possibly an even more major award for contributions to information sciences, and many other awards that I won't embarrass him with. So he's going to talk to us about new bounds in channel coding. And I have also the pleasure of saying that after the talk, we plan to go up and celebrate the last official talk of the meeting with some wine, kindly provided by Ilse from New Zealand Wine. So please make sure to stay till the end. Sergio.
All right, so then I have to budget my time because we have the wine, and then at 7:30 there is a very important World Cup match.
Spain was what game?
Spain against Portugal. So anyway, some of you, it's a very heterogeneous audience here because some of you are experts in information theory, some of you are not, some of you, I think it's on.
No, okay.
Yeah. Yeah, so I think it's just for the recording. And some of you, in fact, were at a meeting in Cairo where I talked about some of this stuff. So for those of you who were at the meeting, some of the motivation is stuff that you already saw there, but the bulk of the talk is not going to be what I presented there.
I can't run away anyway.
Well, but an ant can. An ant can outrun you.
That's why I sat here.
Okay, so in fact, if you've never seen information theory, probably after this talk, I hope that you get the impression that it's not a very difficult subject, and you'll see that we're going to prove some results that are at the heart of the theory of fundamental limits for channel transmission, and you'll see that the results themselves are fairly easy to show. So this is based on a paper that appeared last month together with a graduate student of mine, Yuri Polyansky, channel coding rate in the finite block length regime that appeared in the information theory transactions. So as you probably have heard, Shannon's theory is an asymptotic theory that set out three main problems. The problem of how much redundancy can we eliminate from a source of information and still recover it perfectly. How much redundancy can we eliminate with a certain degree of distortion, which is what we do in analog to digital conversion, video, images, sound, and so on. And the third major problem is how much redundancy do we need to add to information so that we can transmit it through a channel reliably. And we say reliably, we mean with some probability of making an error. Now the theory is asymptotic and tells you that if you are prepared to wait an unbounded amount of time, then the maximum rate of information at which you can transmit is the channel capacity. Okay, and then of course Shannon in 1948 came up with results that enable you to compute this channel capacity as a function of the statistical description of the channel. Okay, so which is just a sequence of conditional probability distributions. Okay, but now you work in any field that deals with asymptotics, and the question is always how relevant are these asymptotics to the real world? And so the question also is asked in information theory, because information theory is not just mathematical theory, but we pride ourselves in the fact that we are very relevant to the practical world. So in the practical world, do systems that are typically operating out there, are they really in the regime that is controlled by these asymptotic limits or not? All right, so it depends. There are systems whose block length is long enough that indeed we are already in the regime where asymptotics are very good descriptors of what you can do. There are systems, like for example wireless, high-speed data, where the packets of information tend to be rather short. And short in our language is something like this, 1,000. You want to transmit 1,000 bits. What is the best you can do? So then, then that's a question we want to address here. And just to motivate it, the three parameters we can play with are the rate of information, as the number of bits that we send, divided by the block length, how many times we use the channel, and the probability of error, the probability that the decoder does not output the correct code word. Okay, so the interplay between these three parameters, what Shannon did in 1948 was to say, look, at that time when Shannon introduced the problem, no codes had ever been designed, good or bad. And he actually came up with a technique of randomly choosing codes, and in fact, he was able to show that by doing that, you can achieve the best possible rate. That's not an actual practical construction technique. It's more of a proof theorem device. But anyway, he showed that if we let the block length go to infinity, while we take the probability of error going to 0, then the rate, then by definition, is the capacity of the channel, and then he showed results on how to compute that. Now, you may be a little bit more ambitious and then say, well, I'm not going to let the error probability go to 0, but I'm going to, as block length now goes to infinity, I'm going to let the error probability, I'm happy with 10 to the minus 3, for example. What is the rate? Can I now get a better rate than I was getting before because I'm not as ambitious? And the answer that you get in that case is what we call the epsilon capacity. But for most channels that behave ergodically, then this C epsilon is the same as the other one. Okay, so if the channel is behaving ergodically, with this block length going to infinity, eventually we're gonna be able, through encoding and decoding, to transform it into a bit pipe that is very, very reliable. So even if we leave ourselves this freedom of being tolerant to a certain error probability, we cannot achieve a better rate for most channels. Okay, so now here's another way in which we can solve this problem. And we can say, well, now I'm going to fix a certain rate. So I'm going to fix a rate R, which is going to be a fraction of capacity. If I fix a rate which is larger than capacity, then the whole thing is going to break down and there is nothing I can do. But I'm going to fix a rate, say for example, half of capacity. I'm going to let this block length again go to infinity, and then I'm going to observe what happens to the error probability, to the smallest error probability that you can achieve with any coding scheme. So that error probability, in fact, is going to go to 0 exponentially fast, exponentially with this parameter n, which is the block length. All right, so this is a large deviations type of result. And what you're interested in, that type of large deviations result, is finding this function, which we call the reliability function, as a function of the rate. All right, so this type of refinement of the capacity result started in the 1950s and has been quite an area of research in information theory. It has attracted a lot of attention. A lot of the practical design in information theory is very much affected by, sorry, not in information, the practical design in the real world is very much affected by information theory, primarily in the capacity sense. Say, how do parameters in a channel affect capacity? Not so much the reliability function. I think practitioners have not been taking advantage a lot about reliability functions. Perhaps one of the main reasons may be that they are very hard to find. And in fact, even for some of the simplest channels in information theory, we still don't know this function for all possible rates. Okay, so let's go back to the question that I posed before. And the question that I posed at the beginning was, what happens if the block length is equal to 1,000? Well, if the block length is equal to 1,000, then I cannot insist that the error probability is going to go to 0. Nothing is going anywhere because the block length is frozen. So I'm going to say, like every designer is going to say, well, this is a certain probability that I'm shooting for. Now, what is the rate? What is the rate that I can achieve with those two parameters? And that's what we're going to call R star and epsilon, the fundamental limit for given block length and error probability. All right, so the short answer is that this is insoluble because it's a very, very challenging combinatorial optimization problem, and you cannot even solve it for baby cases. It's extremely, extremely hard. All right, so the approach that we're going to take is going to be an approach of bounding, upper and lower bounds, and then also approximation, and we'll see that the approximation is going to be quite good. So then if you define the maximal code size as this m star and epsilon, so it is the maximal number of code words that you can find with block length n and error probability epsilon, then you normalize that by, you take the logarithm, so that will be the number of bits in your message. You normalize that by the block length. You let the error probability go to 0, and then you take the lim as n goes to infinity. All right, so that's what we call the channel capacity, definition of channel capacity. All right, so how do we usually prove a result for capacity? That's what we call a channel coding theorem in information theory. So the idea in a channel coding theorem is, this is a definition, this is not a theorem. What we want to do is then find an expression for C that depends on the statistical characterization of the channel. So the structure of those proofs, even if this structure is not always so cleanly separated, as you see in this slide, is that in fact, even though we are interested in the asymptotic regime, in fact, we are working in the finite block length regime. All right, so all the information theory happens in 1 and 2, and the last step is, say, law of large numbers, ergodic theorem, something like that. So the idea is that in the what we call the achievability side, we will find a lower bound to the function. So finding a lower bound to the function entails, in fact, finding a coding scheme that will do the job. Okay. The other, so here in number 2, we have the freedom. Where do we choose our code words? In number 1, we have the freedom. In number 2, what we're looking for is an upper bound to that maximal code size. So then this type of result says, okay, I give you any code, I give you any fixed code, now give me a bound on its error probability. Or vice versa, I give you a code with a certain error probability, and then say you have to give a bound on how many code words, lower bound on how many code words it has. All right, So then, if you're lucky and you've done a good job with this achievability and converse, then you'll be able to show that this sandwich is asymptotically tight. Okay, so before I give you the results, let me show you what's going to happen. This is what's going to happen. This is a typical curve, which is, this curve is obtained for what we call the binary erasure channel. So in the binary erasure channel, you send some bits, and some of them get lost in transit. Okay, so you get erasures. So the receiver knows where these erasures have happened. All right, so here we have a channel which has an erasure rate of 50%, and the capacity of that channel is 1 minus the erasure rate. So in this case, as you can see from here, is just 1/2. That's the capacity. Now I'm plotting the rate of information, bits per channel use, as a function of the block length. So, and the range of interest here is from 0 to 2000. So you see that the approach to capacity is not all that swift, okay? But these bounds that I'll show you today, converse and achievability bounds, in fact, not only are tight at infinity, which is what you would need for this proof of a random coding theorem to work, but the bounds that I'll show you today are actually quite tight in essentially all block lengths beyond maybe 100 or 200. Here, the problem is, of course, that the uncertainty, the vertical uncertainty is becoming quite large.
What is epsilon in this case?
Yes, very good question. So we have to say what is epsilon, because the curves will depend on epsilon. In this case, is 10 to the minus 3. Yeah, throughout the range. Block length, error probability, 10 to the minus 3. Okay, so so then, and this is what I talked about in Egypt. As we will see, the bounds are actually, in general, they are not all that easy to compute, and they tend to be pretty messy. So it would be nice if we can find a nice way to approximate these curves, which gives, first of all, something that would be easier to compute, and that maybe, like capacity, depends in a nice way in the channel.
What about your definition? Is it maximum error or average?
We do it in both ways. Yeah, the naked eye cannot see the difference. Yeah, so yeah, I don't want to get into distinctions because otherwise it gets a bit messy. But you will see in the paper, you'll see that you can do it for both. Okay, so here's the definition of channel dispersion. So as you will see, knowing the channel capacity and knowing this parameter, the channel dispersion, then we can get an excellent approximation in overall that range. So the way you define it, remember, this is going to go, as epsilon goes to 0 and n goes to infinity, this is going to go to the capacity. In fact, even if epsilon does not go to 0, in a channel like that, it's going to go to the capacity. Okay? So now this is going to 0. Now we multiply it by n, which is going to infinity, and then we normalize it by the logarithm of 1 over epsilon. Now, why do we do this? Why do we define it in this way? Well, the reason is that essentially there is a random variable, there is a certain random variable for each channel that eventually looks like a Gaussian random variable. And the fundamental limit at block length n behaves as the abscissa that you need so that the red area is epsilon. And of course, this the mean of this Gaussian random variable is the capacity, asymptotically, in fact, and asymptotically the variance is scaling as v divided by n. Okay, so that's why we define the dispersion in the way that we did. So this Q function, this is just a complementary Gaussian distribution. All right, and this is accurate up to order log n divided by n. Okay, so this in fact is a theorem, and this theorem holds for a variety of channels. We've shown it for discrete memoryless channels, Gaussian channels, and so on. Some other channels too, but in general, you always have this behavior, and then the question is how. Of course, Shannon told us how to compute the capacity, and then how do we compute the dispersion? Before I tell you that, let me just say that an intuitive way to see what is the role of this dispersion is the following. Say the capacity, which would be like a first order analysis, is comparing the channel to a deterministic bit pipe. It's saying, okay, so the channel eventually, if we have a very long coding horizon, is behaving like a flawless bit pipe that operates at this rate, that can admit bits at the channel capacity. Now we're saying, well, we're not willing to wait an infinite amount of time, or more precisely, an unbounded amount of time. What is the required block length that I need in order to transmit at a fraction of capacity, fraction eta of capacity, with a certain error rate epsilon? So then you see that the answer to that question has two factors. One, which is independent of the channel, just the inverse of the Q function divided by 1 minus that fraction squared. So that just depends on how ambitious you are. And this factor that does depend on the channel, the dispersion divided by the capacity square. So the kind of like the intuition behind this parameter is delay. This is delay. Yes?
If I take the more classical approach, which is the error exponent approach, and I do a quadratic approximation of the error exponent curve around the capacity, will I get the same conclusion?
Okay, so in fact I was going to talk about that towards the end, but I can...
because it looks like a curvature. Right?
Yeah, in fact...
So V will be the curvature.
Yeah. In fact, I can... let's just go fast through all the slides and then until I find that. It's easier that I show you the slide rather than I... Oh, this is that now. There is a finite rate at which you can change the slides. Okay, so here's how, if you had, say you are so lucky that you solve for the relativity function, okay, which is a function of the rate, and eraser. Is there an eraser somewhere?
Yeah,
oh, here. Okay, so this is going to be a typical relativity function. So right here, this is capacity. And because, remember, this is the speed at which you go to zero, at which the error probability goes to zero exponentially with the block length. Now, if you look at this type of approximation, which would be, okay, well, let's assume that this is an equality. It's not an equality because this is an asymptotic measure. So this is, let's pretend that this is equal. So then you would say, well, I fix r, I fix epsilon, let me see what is the n that I need to get that kind of performance. So, you know, you could then plot that error exponent approximation, and then you get, for the same parameters that I showed before, you get that curve there, which is the dashed curve. Okay? So the approximation, in this case, is, as you can see, is not as good as this normal approximation.
Different regime, right?
No, I think, Sergio, the picture can be, if you go over there, and you just draw the quadratic.
Yeah, I'm coming.
That's
In fact,
really why.
yeah. You see, there are several things that come into play here. So you could ask, why is it that in one case we get a better approximation than the other? And really, it's the reason why we have the law of large numbers, the central limit theorem, and large deviations. They are all answering different questions. Okay, so in essence, when we go to n equals 1,000, none of these three things is answering n equals 1,000, epsilon equals 10 to the minus 3. So we just have to cross our fingers and say, okay, let's see which one of these three things is more representative of the truth. And the truth, of course, we know lies somewhere between the bounds. So this is just an explanation why you may not get as accurate results with the alternative approach. So one is telling us, well, the block length that is required to sustain a given error rate, a given error probability and given rate behaves like this with epsilon. The other one is telling you behaves like that as epsilon. Of course, this is not very different if epsilon is small, but if epsilon is not so small, like maybe 10 to the minus 2 or something like that, then there may be a difference. Now, of course, the thing that gets swept under the rugs in large deviations is the sub-exponential constant. And you all know that's extremely hard to pinpoint exactly, but it's of course important in the finite block length regime when you have an error probability that may not be all that small. Okay, so going back to what David was saying. When we look at the reliability function at near capacity, it's going to behave like a parabola. And the parameter of the parabola is actually going to be, the constant is actually going to be inversely proportional to the dispersion. Okay, so if we have this reliability function immediately by taking just the second derivative at capacity, then we have the dispersion.
This holds true for already.
No. This holds that we have been able to show for a limited class of channels. Okay, memoryless channels we've been able to show and so on. It'd be great if I could show you a completely general result that would say, okay, here's the definition of the reliability function, here's the definition of dispersion. They are, and this is always true. I don't have such a result. But what
capacity, there's no problem knowing E of R, Jen.
Sorry?
Your capacity, you're okay. You know E of R most of the time.
Yeah, I'll show you examples of how to compute it. So.
Sergio, it is your conjecture that the relationship is true quite generally.
Quite generally, yeah. That's. But here's something. Once I went to Washington, and because my wife had a meeting, and I just went there as a spouse. I didn't know what to do. I had already seen most of the museums, so I went to the Library of Congress to look through Claude Shannon's papers. And lo and behold, he kept a lot of the stuff, a lot of his correspondence and so on. It's really amazing how many people wrote to him asking him about artificial intelligence and so on, and playing chess with computers and so on. Not so much about information theory. So here's what I found. I found a slide I found a piece of paper, undated, that says behavior near channel capacity. For rates R near the channel capacity, the characteristic curve, what he means by the characteristic curve is what we call the reliability function, is parabolic in nature, being given approximately by, and then he writes what I just showed you, sigma square instead of V, but this sigma square, the way he defines it, is, as I'm going to show you now, is just the variance of a certain random variable, which is indeed coincides with the expression for dispersion that we have for the discrete memberless channel. Okay, so it kind of ends here in mid-sentence. Okay, so if you look at the paper that I mentioned, the May paper, in fact, I will reproduce this thing. Not with very high quality, because I brought my scanner to the Library of Congress and they didn't let me use it. I had to use like a photocopier from the 1960s. So. Okay, so with that little parenthesis.
Sorry, okay.
Yeah, go ahead.
My original question was, so if you plug that parabola approximation, you don't seem to get that expression, right?
I think that's
So no. So
this Q minus 1.
right. So that
You get something similar. It seems.
you'll get. So if I could conjecture, I think if you draw the parabola on that curve, you'll see that the results here are actually quite important. You know what you present, because if you draw the parabola, it looks like the parabola is an approximation very good close to capacity, but a overly optimistic approximation away from capacity. And so the reliability function is sort of being more careful in the reliability function view. But I think what your curve shows that actually it's being paranoid. That actually that quadratic actually holds effectively in terms of governing that the numbers out. Further.
well, it's a bit hard to get carried away with that one, because you see, like for example, when we look at a result like this, then say we're here at I don't know, 500, right? So if we're at 500, we are not necessarily very close to capacity already there, 0.42, 0.43. Okay, so we may be around here. So one thing is the effect that we're making an error by making this parabolic. But if you want, the Gaussian approximation is making that error too, because it's based on the fact that it's thinking everything is Gaussian. That's one of the source of the errors, and the other source, of course, is that n is 500. So the thinking that we get by one versus the other, by one asymptotic versus the other asymptotic, may not have the same effect for fixed block length. Okay, so so this is the result that I was saying, that when you have a memberless channel, the capacity is, let me write here, this random variable is very important. So in channel coding, this random variable ixy this is going to be the logarithm of the derivative between the joint distribution of the input and the output and the product of the marginals evaluated at AB. Traditionally this is called the information density. So if you take the expectation when you replace A and B by X and Y, if you take that expectation, then you get the mutual information. All right, and if you take the best distribution at the output that maximizes this expectation, then you get Shannon's formula. You get the capacity of the channel. So now, imagine that of all the distributions that achieve that maximum, the maximum mutual information, you look at the variances of that random variable, then you choose the minimum of those. Then that's going to be the channel dispersion for discrete memoryless channels. Now, ordinarily, many channels of interest, there's just going to be just one distribution in that minimum. So we just have the variance of whatever the distribution is. So then, as a simple exercise, then you can compute that that dispersion. Now, what is interesting is that remember that originally I had said that in general for discrete memoryless channels and also some other channels like AWGN, you can prove that the remainder here is order log n divided by n. But in certain cases, you can do better. For example, for the binary error channel, you can prove that that is order 1 over n. And then this v divided by c squared looks like delta divided by 1 minus delta, okay? Which sounds like delay to me, right? Of course, as the erasure rate increases, this thing skyrockets, right? As the rate of erasures becomes higher and higher, not only you have to add more redundancy to the data so that it gets through, but you have to wait more to the channel to become typical. Okay, so the randomness in the channel, the fluctuations, the random fluctuations in the channel have higher and higher variance. Okay, so that's essentially what I showed you before when it had the error exponent approximation. And this is you see there that the normal approximation is quite good in that case over a very large range of parameters. All right, so now.
Can you go one slide?
Yeah. This one?
No, this, the one
Yeah.
right. Well, this fact you think is holds only for binary erasure
Yeah.
or general?
No. This is only for the binary erasure channel. I'm going to show you some other examples now.
So for other channels, this limit may not be.
It's not.
It may be finite.
Well, let's see. Here's what happens with the binary symmetric channel. In the binary symmetric channel, here, instead of getting erasures, you get errors. And you, in fact, don't know where the errors are. Okay? So you get errors with error rate, with rate delta. So then you do the calculation, you get that expression as a function of delta.
So a comment here actually. So with this, when epsilon is on an exponential scale, then actually the log n over 2n will dominate the middle term, right? So this, I mean, you're
Oh, okay. So now yeah.
So this is actually completely orthogonal to error exponent asymptotics, and then the previous.
Yeah. Of course. Which is why if you want to do large deviations, don't use the central limit theorem, right?
But your previous formula had a kappa of 1 over n, so that was sort of more on the same scale. That's
Yeah.
what this quadratic thing was about.
Yes.
But here this is away from that regime altogether.
Yes. So there you see a case where indeed we had order log n divided by n, and in this case we cannot improve that. That is there. All right. So I'm in the market for a name for this constant here in front of the log divided by n. Log n divided by n. I don't know what to call that.
Huh?
Uh-huh. All right, so let's see how this looks like for the binary symmetric channel. Again, we see that, in fact, this explodes much faster than delta divided by 1 minus delta. So I'm showing here the BEC just for comparison. You know, it doesn't look right because this actually is exploding. Well, it is right because it's exploding for delta equals 1, okay?
It's even going to be higher if you normalize for the same capacity.
Yeah, I should have done that. I should have done that because this is comparing apples to oranges. Yeah, so what does delta have to do with the erasure rate have to do with the, that is just for, you know, just for fun. So anyway, oh yeah, I wanted to show you here the bounds and the approximation. So the bounds are actually what I'm going to show you next. And if you look at them, it sounds like you don't want to hear it, right? Because they are so complicated for even the simplest channel. But these are, the bounds themselves are going to be actually quite easy to describe in general. They become messy when you want to apply them to specific channels. Okay, and there's the Gaussian approximation.
How do they relate to Sloan's tables and so on?
To what?
Well, there are best codes known in many of these cases.
Oh, you'll,
Yeah, so
yeah, no, but that's old-fashioned. I'll show you.
But they also have a range, I guess. Is that much smaller than your bounds is the question. They've actually found the best codes for many cases.
All right, so let me show you. Let me show you something about that. So this is the curve for the AWGN. Okay. Now again, you see kind of like the same shape over and over again, and then you see this green curve. That green curve is a curve for the multi-edge low-density parity check codes with a belief propagation decoder that were optimized by Tom Richardson, who is one of the world's expert in how to design these sparse graph codes. So you see that those codes are far away from capacity by a gap, and the gap, half of the gap is bridgeable by being smarter and putting more complexity inside your encoder and decoder, but the other half is not bridgeable. It's just fundamental. Okay. Now, this one plots many different codes here that have been used for the space program by NASA, by JPL, and also we put these multi-edge LDPCs of Tom Richardson. So what am I plotting here? Now here this is block length, probability of error is 10 to the minus 4, and here this is normalized rate. What do I mean by normalized rate? Well, what I mean by normalized rate is the rate divided by not capacity, but the finite block length capacity. Okay? I don't have it. I don't have. I only have upper and lower bounds. Well, the surrogate is the Gaussian approximation with the dispersion. Okay. So the multi-edge LDPCs are pretty darn good, but some of the turbo codes come also very close to that.
Missing a complexity axis.
Next year. So, okay, so let me just make a point here because it's an important point. So before I forget, maybe not in this curve, in one of the others. Okay. The point is that the best achievability result, well, let me use the binary erasure channel here. The binary symmetric channel. So the best achievability result, in fact, here, this is obtained through a technique of random coding. It's not the same argument that Shannon used, but uses the technique of Shannon. It says, okay, I don't know how to construct a good code. I don't know how to construct a bad code in 1948. Let me choose all possible codes at random with the same probability, find what is the error probability, the average error probability, and then there must be a code among all those that is at least as good as the average. So that's what he said. And in fact, coding theorists, of course, coding theory started also in 1948 because Hamming's paper, or the Hamming code, actually started at the same time of Shannon. Coding theorists said, okay, that's a proof technique, let's forget about that. Let's be nice and do geometric designs that are beautiful, and let's get obsessed with minimum distance, with correcting a given number of errors. So they took that path. And for a long time, they were saying, this Shannon stuff, this is science fiction. You would need exponential complexity. If you actually want to know what the practical limit of a channel is, there is this other parameter, and so on, and this is what you should look at. So all of that that folklore was actually disproved pretty recently, in the 1990s. Some French researchers that were really essentially simulating stuff, not necessarily based on a lot of theory, came up with these codes. At the beginning, nobody believed that they were as good as they claimed, but indeed, these turbo codes were very good, and now the state of the art in coding theory is based on sparse graph codes. So the codes actually are a very nice balance between the complete randomness that Shannon predicted would be good, but also structure, because you need a structure. If you don't have structure in your code, then how are you going to encode it? You cannot have a list of all possible code words. 2 to the 1,000 code words. We cannot have a list of those. And you also need a structure in the decoder. You cannot use a maximum likelihood decoder because it would be unthinkable. So then you do sparse graph constructions, random-like constructions, and you have suboptimal decoders, belief propagation decoders, that are near optimal. So what is the point that I want to make? Well, the point I want to make is that since this bound, this achievability bound, is actually with the technique of random coding, which supposedly is representative of the sparse code structure, so to speak, you see that random coding actually, for finite block length, is not optimal. It's optimal asymptotically. Shannon told us that, but for fixed block length, it's not. You can do better by not doing random coding. But you cannot do a lot better. It's already very close to the converse. So you cannot gain much by being geometrical. Of course, that is up to a point, right? Because when you are here, if you are designing a code of block length 10, then you want to be geometrical. Then you want to, not choose your code at random, even though at very low block length, you could indeed choose a code at random and just encode it easily. But there, of course, that's when random coding starts losing big time.
Yeah, but you're using the word random coding in a very loose sense, I think. Because to get your lower bounds, you have to be doing some kind of exploitation.
No.
You have to be able to you have to be separating your code words through the process of what you call randomization. I mean, what do you mean by random coding to get your lower bounds?
You'll see. I haven't got to that point yet. But I'm using it in the sense of Shannon. The sense of Shannon, which is what I just said. Choose all possible codes with equal probability.
So then you're going to get code words getting too close to
You choose
each other.
digits independent.
Eh?
You choose digits independent.
Exactly. I mean,
I'm not information serious. So what you say is that all these fancy coding techniques are meant essentially for complexity issues, but in terms of error exponents, even in this short scale of in this scale of looking at finite block lengths. You do in all these channels you have shown us, you do better with in terms with random codes than with LDPC or with turbo codes.
Well, but this is, don't forget, this is the best. So this is an achievability bound that tells that is achieved through a random coding technique. Okay, so it's saying, okay, so if I average over all possible codes chosen at random, this is what you would get.
It's an ensemble result.
Yeah,
You still have the problem of finding things.
Okay,
Yeah.
then you still have to. Okay, so it may be that some of them are very bad. And
Yeah, so the typical thing in coding theory is also that all codes, okay, so most codes are good except those we can find. Okay, so the problem is that once, what does it mean to find a code? We don't throw darts at a real line and then that's a code. We have to describe it with some structure. And what has happened up until very recently, there is a new class of codes called the polar codes that have a pretty easy, simple description and are capacity achieving. Up until recently, if that result had appeared in the 50s, it would have been a revolution. They are not, if you plot them here, they are not going to be very good. Okay, so there is not, those codes are not particularly a good choice in practice, but conceptually they are quite nice. Okay, so your question was, still, the state of the art is very far away from what a monkey can do, right?
That's what I said.
Depends on which monkey.
Okay, so well, let me understand what you were asking.
Right, so, but I understand these are ensemble averages, and so
Yes.
you have from this ensemble average to pick. So assume you would draw one code at random and you are interested in that. So maybe it's very bad, but so what you know is the average, or
Yes.
well, if you average over all these random configurations,
Yes.
and look this ensemble average, it beats I don't know, turbo code.
Yes.
That's not surprising. That's not surprising.
No, that's okay.
With maximum likelihood decoding, of course.
With maximum likelihood. Okay. And that, so essentially so you still have an algorithm which will produce one, because I mean, if it's an ensemble average, it means that if you pick sufficiently many samples independently, you will find one which is good, right?
Yeah, but the problem.
Many can be very low.
It's not describable.
Exactly.
Describable. It's just
Okay, right.
Because in order just to analyze the error probability of what you have
You have
chosen,
an algorithm on this.
you have to run an algorithm that is of an unbelievable complexity. But what you're describing, you could do, say, for block length equals 10, you can do.
Okay.
so this.
But in fact, for block length equals 10, in fact, for any block length, I'll show you a result where I have an exact error probability for random coding, exact analysis of the fundamental limit for random coding. So you don't even need to do that.
So this new class of codes that you mentioned, polar codes, are they proven to achieve the capacity?
Yes. Yes.
But they have square root of n exponents.
Square root of.
Yeah, they're not like e to the minus n, right? They're probabilities. They're still square root of n.
E to the minus square root.
E to the minus square root of n. So that's
I mean,
what.
there is a bound of this.
Yeah, but it's sort of not on the same scale. It's much larger on that.
Yeah. So
So the bound is believed to be touched that you mentioned.
I'm not entirely sure. I don't think people know yet.
all right. So another interesting issue with capacity is that with dispersion. I'm illustrating it here with the Gilbert-Elliott channel. Is that many times for channels that have fading in information theory, the capacity does not depend on the fading dynamics. It's just transparent to the fading dynamics. Why? Because eventually you wait so long that you're going to see everything, and you're going to see it many times, and you're going to code through those statistical fluctuations. But it certainly is going to matter as far as the finite block length behavior. If you have a very slow fading channel, then you'll have to code for a longer time just to make sure that you are not in one of the bad periods. Okay, so it's very important, and there's been a lot of work, some of it by people who are in this room, but the dispersion then does indeed capture the dynamics. Here we have a very simple channel where you have two binary symmetric channels, a good one and a bad one, and you alternate as a Markov chain from one to the other. The capacity is just the average of the two capacities, and the dispersion then does indeed depend on the dynamics of the channel. So as tau goes to 0, when you get stuck in the same channel for a long time, a slow Markov chain, then the dispersion blows up. Okay, and
In this example, if I look at a block, so if I think of the mutual information as a random variable as a function of the channel state, I'm thinking from an engineer's point of view. Then I have a random variable. Is V the variance of that random variable or no? Or something more subtle?
yes, yes, it is the variance of that random variable. Yeah. All right, so here's for the AWGN. The AWGN, that means additive white Gaussian noise. The dispersion depends on this is Shannon's famous formula for the capacity. So the dispersion depends on the signal to noise ratio, as you can see here. The parameter here, the thing that was 1/2, is now alpha, and unfortunately I can't tell you whether it's 1/2 or not, but I know that it's not larger than 1/2. So that's how the curve, the delay curve looks like. As the channel becomes better and better, not only you can send more bits of information, but you need to code through a longer horizon, through a shorter horizon, sorry. Okay, so it looks like time is up and I have not started to talk about what I wanted to talk yet. So what should we do?
Go for another 10
Is
minutes.
your line far away?
It's not very far away. So
Bring the one.
Solution is obvious.
If you are okay, I can continue.
I think 10 minutes would be useful, yeah, because
I hate to go over time, but I think I got a little bit
We asked
too worried about
Yeah.
We
the
asked
people
for
who were not information theorists, and I put Venkat to sleep. I had to wake him up with a laser pointer.
eyes are burnt out, yeah.
Okay, so now it becomes a matter of just trying to pick and choose maybe one thing so that you get an idea. So anyway, these are the classical achievability bounds. So in 1948, Shannon really didn't give a proof. Not even close to a proof, even though he said, okay, there is this random coding idea and so on. So the main ingredients were there, but it was not until 57 that he, in fact, gave a proof of the achievability bound using random coding. All right, and the bound looks like this. Now, by the way, very important thing here is that you see n does not come into the picture. Okay, so what happened to n? Well, this is really how I teach information theory. When you do the finite block length analysis, before you go to infinity, so what you have are vectors that are mapped to vectors, right? So the fact that you have an nth Cartesian product here is going to play no role whatsoever in the derivation of the bounds. Nothing. Zip. Okay? So might as well think that I'm analyzing just just one random variable x, another random variable y. Okay, and we have some random transformation here, py given x. Okay, now of course, when you go to apply the bounds, then that will be a random transformation that will map 1,000 bits into 1,000 bits. Okay, or whatever. But it just messes up the notation by having to carry all those superscripts n everywhere. All right, so so what you can see is two things. Well, first of all, the thing that is key in the bounds is no longer the mutual information, but it's really the CDF of the random variable, not the expectation, but the CDF.
I the density or
Yeah, is this one. Yeah, I don't have the subscript here, xy, in the interest of. Eh? Well, that's a very good question from a Greek. Yeah, in fact, what I like to use is this. In LaTeX. And that, I don't think it's iota, but it's like an I without the dot. Because you never know when you may want to take the derivative of information density. Okay. Okay, so this was, if you think about it, this bound and this bound are almost exactly the same because you're just rearranging m and epsilon and beta here. Eventually it's the same thing, except here we have m-1 rather than m. Anyway, so I was saying, Shannon then showed this rigorously 57, Feinstein 55. This was regarded to be the first rigorous proof of the channel coding theorem. Completely different approach. It had nothing to do with random codes. It was more of a greedy approach. And then Gallagher in 1965, then again using random coding, but Gallagher was very much not just he wanted to get a bound that would be good for proving channel capacity, but a bound that would be good for the reliability function. So then he came up with this bound that in fact uses the maximum likelihood decoder, whereas these ones here do not, this one here does not. Actually, his proof does use the maximum likelihood decoding, but this is a very difficult proof, but you can prove it much easier. Anyway.
About is better, Shannon's or Gallagher's?
Yeah, I'll show you some.
What is this y tilde or y bar?
Yes, good question. This is an independent copy of y. So x and y here have that distribution, the joint distribution at the input and output, and then y bar is independent of x, but with the same marginal as y. This is not the form that you people are used to, but it's the same if you put it in terms of the information density. And there are other.
But two bounds, I don't think they're comparable universally.
Excuse me?
Shannon bound.
No. Yeah, I'll show you some examples of that. Okay, so this is a nice result because it gives you an exact expression for the random coding error probability. So these, unlike the results that are around, which give an upper bound to the best thing you can do. An upper bound to the average error probability. This gives you the exact error probability. The problem here is that the computational complexity is m. You have m here, and then you have a combinatorial number with m, and m is exponential in the block length. So, if you want to compute this for n equals 1,000, good luck. All right, so here's, we have essentially two bounds, two achievability bounds. One is the random coding union bound. And here what we do is, along the spirit of this bound that I flashed before for not bound, the exact expression for the for random coding, you condition on X and Y. You condition on the input and output of the channel. And then again, you have X bar, which is an independent copy of X. All right, so this is in fact very simple to prove, but it refines the upper bound in the sense that you limit the damage that large terms introduce into the union bound. Essentially, if you have something that is greater than 1, then you know that you can upper bound it by 1, and then you take the expectation. Now, this is using maximum likelihood decoder, random coding, union bound, is tighter than the classical achievability bounds. Problem is that it's hard to compute except in special cases. So when you have, and this is true, of course, always, that if you can exploit symmetries, then you're going to do better. And then this other one is what we call the dependence testing achievability bound. Also is in terms of the information density. This one is easier to compute than the RCU bound, and it's easier to analyze the asymptotics. For example, from here you can immediately see that you can show that the best rate is lower bounded by capacity. So as n goes to infinity, then this becomes xn yn. You normalize by n, and then you see that if your information density if the rate is below capacity and you're using an optimum input distribution, then this is going to be positive and your epsilon is going to be going to 0 exponentially fast. Okay, so let me show you the proof of this bound. And the bound combines the Shannon random coding idea with the decoder, which is inherent in Feinstein's suboptimal decoder. So we're not going to use a maximum likelihood decoder, but let me tell you what a maximum likelihood decoder would do. So what you want to do is you compute the information density. Y is the received observation. That's what the decoder gets. And then you compute that information density for each possible code word. All right, so you have m possible code words. You find that sometimes it may be negative. Okay, this logarithm may be negative for some code words. And then the maximum likelihood choice is just the code word that achieves the maximum. So that's the maximum likelihood decoder. Here we'd say 6. What Feinstein does is says, look, we're going to, since this is going to be actually very hard to analyze because there is coupling between these random variables, we're going to put a threshold, and then I'm going to decide that the message is the first number that is above the threshold. Okay, so then you choose, according to the Feinstein decoder, then you choose that one. Now, another thing that you can do, and that's indeed how the easiest proof of the channel coding theorem, is by saying, well, if there are more than one, if there is more than one information density above the threshold, then I give up and I say there is an error. Okay, so in that case, there is an error. So that decoder is not as powerful as this one, let alone as the maximum likelihood decoder, but with that decoder you can prove the bound that I labeled Shannon. It's not the way he proved it, but it's how you can prove it. Now, in the conventional way that information theory is taught, which is using a leading textbook by Cover and Thomas, you don't have one threshold, you have 6 thresholds. So it's it's not the easiest way. Okay, so why do we have 6 thresholds? David is now mesmerized. So that proof says you have to be typical according to the entropy, individual entropy, the individual entropy of the output, and the joint entropy of the output. So, and being typical means that the equivalent of this is not too low and not too high. Okay? So, the thing of doing it with entropies rather than with information density is a bad idea. You only need to do it with information density. And the thing of saying, well, if it's too good, then I also declare an error, that's a silly thing to do. Okay? We are used to doing that, but it's completely unnecessary. Okay? So all you need is just a little threshold. Okay, so here's what we do. We say, well, in fact, the probability of error when the true message is J is the probability that with the true message you don't go above the threshold, and that's here. And it's the probability that one of the previous guys that are numbered less than J actually is above the threshold. But those guys are really transmitting with different code words, okay? With code words that are not the true one. All right? So, in fact, you can show that you have this kind of relationship. Now, when you take the average with respect to all the code words, then you get this becomes m minus 1 divided by 2. And then now you have to optimize with respect to the threshold. And the optimization with respect to the threshold in the typical Feinstein and Shannon problems, you see, you always have this thing that you have to optimize. Even also in Gallagher's example, you have something that you need to optimize. Whereas in this bound, in the DT bound, there is nothing that you need to optimize.
We have the non-information theorists, which probably wrap up that.
Yeah, okay. So, so let me just give the punchline of that particular proof. You don't want to cut me off in the middle of the proof. So now, what you see here is you recognize that this is in fact just the error probability of a Bayesian testing between dependent distributions with pxy and an independent distribution px even y. So we just choose the optimum threshold for that binary hypothesis testing problem. You can find it in Prof's form. You cannot do it with the other bounds. And then this is just a matter of rearranging the terms and just doing a change of measure argument, and you get the bound. So there is a pending question here about, you know, how do all these bounds compare? And I'll just show you one of these curves. You see here the green one with dotted, that's Feinstein. Sometimes Feinstein beats Gallagher, okay? And here, in this particular case, the best of these bounds is the DT bound, the one that I just showed you the proof, the DT, the black one here. The RCU here is worse, but it's very close to the DT. And sometimes it's the other way around. Okay. So Gallagher, in fact, becomes good, better when you are farther away from capacity. So when you have, in this case, for example, it may even beat the DT bound. It cannot beat the RCU bound. Okay, so I stop here.
Plenty of questions during the talk, and it's a small audience, and Sergio's around all day tomorrow, so let's leave the questions for later.
Yeah.
And proceed to the wine.
So this is the answer to the question.
And since this is the last seminar of the program, I think it would be very nice to thank the organisers for setting up such a wonderful program, for all the hard work that you've done, from which we've all benefited very much. Thank you very much.